To warm up. Now, what's due? Academic inquiry. Away. We need to focus on chemistry today. But if you do have any last minute academic inquiry as my assignment, like, looking okay questions, I can give you a brief over, but not a draft look or anything like that. I can say, yeah, hand it in. Okay, so, but not now, because now it's chemistry. But the cool thing is, I'm going to give you a warm-up activity.
Oh,
so,
no.
turn to page 48. Page 48. We have some. Sorry. No, that's too much. The white papers that I gave you, white pages. Okay, on page 48 you have bonus questions. So those bonus questions are just revisiting a little bit about systems, a little bit about structural organization, as well as directional terms. So I want you to spend the next, say, six to 8 minutes trying to answer these. Some of you might have done it already if you're super duper. If you have, I want you to attempt to do compulsory homework quiz 2, because that is due next week. How many of you have done it or finished it? We've got 1, 2, cool. Okay, so you're going to start working on your quiz. You get a bit of a head start. It's all on chemistry, so you'll love me for it. But the rest of you, I want you to start on that. Yeah.
I don't know chemistry.
Okay. Okay, are we pretty much finished? All done? Oh, done. Almost? Okay, let's go through those answers. What's the time? Yeah, you've had enough time.
Okay.
Okay, so, who wants to give me, why would you have a hard time learning and understanding physiology if you don't understand anatomy? Who wants to give me the answer? Give it a go. Which you have to come to. Go on, Johnny, you look like you're
Because you can't, you need to know where the position of each organ is to be able to understand how it actually works together.
Good. Exactly. You can't explain the functioning of the heart if you think the heart's in your toe. So you need to understand the organ, where it is, its structure, to be able to understand how it works. Well done. Okay. Kidney function, bone growth, heartbeat are all aspects of anatomy. True or false?
False.
Because they are? They're all? If they're not anatomy, they are? Physiology. Thank you. Okay, at which level of structural organization is the stomach? Organ. Good, because the stomach is an organ. At which level of structural organization is a glucose molecule? Chemical. Good. So we're going to be looking today at atoms and molecules and bonds and, as such, glucose molecules. Which system includes the trachea, the lungs, the nasal cavity, and the bronchi? Respiratory. Good. What was it? Respiratory. Okay, so directional terms. The heart is located what to the diaphragm?
Superior.
Good, superior. Okay, the muscles, so this is a little bit tricky and can take 2 answers. So the muscles are what to the skin? Inferior. Inferior would be correct. Another word would be deep. Okay, because inside the body, so your textbooks call it deep, the essentials. The anatomy and physiology, also Marriott calls it inferior, because if you look at a wedge of skin, so when we study skin, we'll study it as a wedge. I know it's not a wedge, but you kind of look at it like that. So your skin sits on top, the muscles are below it, hence inferior. When you're thinking of it in this regard, then it's deep to the superficial layer of the skin. Okay, so that's just different terminology. Right, the shoulder is what to the elbow? Shoulder? Proximal. Good. Yeah, so good. So whatever is said first. In anatomical position, the thumb is? Lateral. Good. And the big toe is?
Medial.
Medial. Good. Because we're wrong way around. Because remember, we don't roll out our feet and our hands, otherwise we look like penguins. Only your hands. You still look like a penguin. So if you got that wrong, you all have to walk around in anatomical position for the rest of the day. Okay, The vertebral region, so your vertebrae, all the way down, is what to the scapular region? Your shoulder blades.
Post. Medial.
So
Posterior.
vertebrae here, scapula here. So vertebrae start there and go all the way down.
Medial.
Medial, good, because your vertebral column or your vertebrae is slap bang on the midline. Okay, oxygen. So we know it's a main element, and we're looking at our main and trace today. Oxygen as a main element. Why is it important? Why is it so important? Because it's what? Part of the respiratory system, okay. What else? Yeah?
Is it that it's necessary for gaseous exchange? It provides energy to cells for aerobic and anaerobic respiration, which produces ATP or biological energy in cells.
I love it. Well done. Okay, so most specifically, in summary of that beautiful answer, go with energy production. Great work. It's part of gaseous exchange, so oxygen and CO2 out, but that's not why it's needed. It's needed for the longevity or the survival of cells and for energy production. Okay, those two things. Right. The sternum is what to the spine? Anterior. Beautiful. The brain is what to the spine?
Superior.
Superior. Good. The brain is superior to the spine. The lungs are to the scapula. So lungs, look, the lungs sit here. Lungs there, scapula there. So the lungs are?
Superior. Anterior.
Sorry?
Anterior.
Anterior, that's the word. Look, lungs there, scapula there. Lungs are in the front, scapula in the back. Where are we? Right. Bicep femoris. What do we know about this muscle? If it says bicep femoris,
Of the leg.
femur, exactly. And remember, do this. You've got two lots of biceps. So if it's got femur in the word, it's going to be on the femur. So it's at the back of the leg. So bicep femoris is what to rectus femoris?
Posterior.
Posterior. Lovely. Bicep femoris there. Rectus femoris here is at the back side. And then last but not least, in anatomical position, the radius, which is in line with the thumb, is what to the ulna?
Lateral.
Lateral. Good. So,
Sorry.
that's okay. Well done. Okay, turn in your workbooks now to the nervous system, which was on page, page 44.
Oh, you have your one?
Sorry guys, won't be a second, I just have no pens, but it's two more. Woo, thank you.
I just copied what's here. And then now.
Right. Your workbooks look something like this for the nervous system. Okay. Now when we're talking nervous system, we're talking about every integration center. And we know it's a fast-acting control system, but it comes from electrical impulses. Okay, and we're looking at chemistry today, and we're looking at energy. And so we're going to look at electrical energy, which comes from the nervous system. Okay, so we've got to have a little bit of an understanding of nervous system. Unfortunately, we don't go into it very much, just as much as this. But it's fascinating, and it's huge. Like the amount of knowledge you gain from studying the nervous system kind of explains a lot in the body. Okay, but you need the basics here, and then we'll progress and progress. And when you do your bachelor, it's a huge big picture stuff, so it's really fun. Not this diagram, but you will need to be able to explain the function of the nervous system. Okay, so this diagram is just for your understanding of how the nervous system works, and we will kind of lean on it with other systems as we go. Okay. First and foremost, though, some of it you'll kind of know anyway. 5 senses. What are our 5 senses? Touch,
Vision,
taste, that. Okay, so we've got 5 senses. So those 5 senses are continuously sending information to our brain. So we all commented on the fishy smell just before. So that information was going to the brain processed the information, and what did you do? You moved the rubbish bin. Okay, so the information went brain, can be various parts of the brain. So we learned about the hypothalamus for thermoregulation last week, but it can also be the pons, it can be the medulla, it depends on what sense we're talking about. And then the control center or the integration decides what action needs to be placed, done, and then sends it to where it needs to go. Okay, so essentially our 5 senses are part of what's known as the sensory pathway. Okay, so sensory. So the sensory path receive this information and send the information to the brain and spinal cord. Okay, now towards the side of that you have 2 boxes. The first being the descriptor for the brain and spinal cord, and that is the central nervous system. So our central nervous system is the controlling aspect. Our central nervous system is the brain and spinal cord. It is central to everything. Okay, so all decisions are made via the brain and spinal cord. Okay, now from our senses going to brain and spinal cord, they indeed need to relay the information on to the motor pathway. Are we working or are we playing? Working? Working? Okay, so information then comes down to the motor path. And just like a motor car gets you from one place to another, so too your motor path is going to deliver the impulse to where it needs to go. Okay? So you need to put this in and stop pulling on the path. Okay? So, motor path is going to deliver the impulse. So as you know, nervous system has 2 aspects. You either have control or you have no control, and that's a good thing, because you don't want to have to wake yourself up at night to make your heart beat, or wake yourself up at night to make yourself breathe, or wake yourself up at night to remind yourself to release cortisol to wake you up in the morning, things like that. Okay, so that there's some parts of our nervous system that happen involuntarily, thank goodness, and there are other parts that we have the control. For instance, you had the control to close your laptop, you had the control to take a sip, you had a control to put on a jumper, whatever it might be. And that is called, so from the motor path, we have what's known as the somatic. It's so dramatic, isn't it? Can't stop. Never said anything hard. Okay, so the somatic nervous system. Anyone know what soma means? You might have done the human development already. No? Okay, soma means body. So remember that, because Vanessa's probably going to ask you, and then you can impress her by saying, oh, it's body. Got it. Okay, so somatic nervous system. Soma means body. This is the part of the nervous system where you have the voluntary control. You decide. Okay, so this part is all voluntary. So what's the definition of voluntary? If you were to explain to me what voluntary meant, you would be like?
It's something done by choice.
Yeah, you choose to do it. Good. Okay, so somatic nervous system, everything that, whether you walk, run, pick up a pen, chew food, swallow, all of those processes are voluntary. However, what happens from there is a division. So from the motor pathway, we also have what's known as the autonomic nervous system. look at the word autonomic, what does it make you think of? Exactly, automatic. Hello, ladies. Exactly, automatic and involuntary. Okay, so those are all of the aspects that I was just explaining. Heartbeat, breathing, hormone release, all of the lymphatic circulation, cardiovascular system, etc. Okay, everything you don't need to control. But then it's further divided into two parts, depending on the scenario, depending on where you act. Okay, so these further divisions, this actually has more divisions, but we'll just stop at these two, are the parasympathetic and sympathetic nervous system. So those are our final two divisions. Now, you've probably heard of these terms a little bit maybe before. For instance, the parasympathetic nervous system has a little term that goes with it. Anyone know what it is? It starts with R. And when I say it, you're going to be like, oh yeah. Have you heard of the rest and digest nervous system? Oh, maybe not. Okay, anyway. Parasympathetic nervous system, rest and digest. Rest and digest. Okay, well, you might have heard the next one then. Sympathetic starts with S.
Fight or flight.
There we go. You see, you have heard of it. Fight or flight. Okay, so you've heard it one thing.
First time I heard
Was
about
it
it.
Amy?
She makes them fight.
All right. Oh, okay, yeah, so you touched on it already. Okay, so our parasympathetic nervous system is our nervous system that controls our rest and digest element. And unfortunately, because of the environment we live in, we primarily don't utilize this nervous system enough. For instance, we live in an environment where it's go, go, go. You know, you go home 3 times in the day, or you leave college, or you have to sit in traffic for 5 hours or 2 hours, or whatever it might be. How many of you guys eat breakfast at a table? Okay, well done to you too. Most people tend to eat up and go and then drink up and go in the car, or in traffic, or take toast on the road, or whatever it might be. We're kind of pushing ourselves at a faster pace, living in a city. As a result, unfortunately, we're not recovering sufficiently. So every time you do any sort of exercise, your muscles develop little microfiber tears. And those little tears have to repair. And the best time to repair is during our rest and digest phase. Okay? And if you're not giving your body sufficient time to repair, you don't repair properly, and then that's when you can slowly allow yourself to get sick or whatever it might be. But essentially what the parasympathetic nervous system is, for instance, when you eat a big meal, you know how, let's over-dramatize it. If you know how Sunday roast, and you eat massive amounts of Sunday roast because it's spectacular. My mum cooks like lamb roast every Sunday. So good. So I always overeat. So consequently, after lunch, I can barely move because I've eaten way too much. And you know how when you eat way too much, you feel really, really fatigued, you're really tired, and you just kind of curl up on a couch somewhere. You don't necessarily sleep, but for a good 15 minutes, you just kind of want to lie there. And then all of a sudden, you get your energy back and you can go again. Have you all experienced that sort of scenario? Okay. So that type of feeling is actually because of something called blood shunting. Your body has the ability to move the blood or shunt the blood to where it's needed. And that, in that situation, it would be shunted to the digestive system. So as the body digests the food, the blood is taking those absorbable units of glucose into the blood and then will be distributing them where it needs to go. But the majority of the blood would be in the digestive organs, and limited blood is in your brain and spinal cord. So that means not enough oxygen getting to the brain, and that's why you feel fatigued when you have a large meal in your stomach, because not enough blood getting up there. Yeah?
So I find something to do with like QI energy and
Okay, so I'm not. Is it key? So if that's what it is, I mean that's. Oh, I don't know. Anyway, your body takes a lot of energy to warm food up. So like, I know some diet plans recommend you have icy cold water first thing in the morning because your body can't handle that. So the metabolism picks up very quickly to warm the water up to help digest it. And you said you eat quite a bit, don't you? And you just maintain a constant body weight. So obviously you don't want your metabolism to be too fast because the minute you have too much cold things, your metabolism is working overtime to try and pick up, kind of warm up the food so your body can process it. So it might be along those lines, I'm not too sure. But essentially, in order for your body to rest, it needs the food to be digested and processed and get into the bloodstream, and then the blood reshunts to where it needs to go. And the same would apply, the old wives' tale about you shouldn't swim when you've eaten. I mean, it's not 100% accurate, but there is some truth in it. Because if you have a big meal and then go for a swim, because your blood supply is primarily in the digestive area, it's not in your muscles, and that's why your muscles will cramp because they're not getting enough oxygen. The funny part is though, the minute you walk, let's say for instance you're on a beach, you're having fish and chips, overeaten, and then you walk from the grassy area where you were eating fish and chips down to the beach. Just that walking motion actually stimulates blood flow back to your muscles. It's like a warm-up. You know how when you exercise, they say you've always got to warm up to increase blood flow to your muscles? So that warm-up actually reshunts the blood back to the muscles. So really, you shouldn't really get a cramp in that instance. In contrast to if you were sitting on the side of a swimming pool eating huge amounts of fish and chips and then just rolled in, then it would apply. Okay, because you haven't actually allowed flow. Or you're sitting on a lie-low eating and then you just fall in. So there is some truth in the matter, but any sort of movement prior to getting into the beach would actually increase oxygen flow to those muscles again. So you shouldn't cramp. I mean, there might be circumstances where you do, but essentially that blood chunk should have returned to the muscles once again. Okay. Now, every evening when you slow down, so you get home from college or from work or whatever it might be, and you slow down, you've had dinner and you kind of collapse on the couch, that is when your parasympathetic nervous system is really kicking into gear. It makes you slow down, it really makes those muscles repaired, makes all of the blood deliver its necessary glucose and oxygen to where it is meant to go. And that's why we said sleep is such a beneficial aspect and why you actually burn more calories sleeping than you do watching TV, because even sleeping in those REM cycles are more beneficial to the repair in the parasympathetic nervous system. Okay. Now the sympathetic nervous system, in contrast, is your fight or flight nervous system. So this one comes into play like all the time. Okay, so we use it to get us up in the morning. We use it to go for a run. We use it to help us perform in a stressful situation. So if you guys are feeling really stressed about your assessment tomorrow, or you have been working non-stop on your assessment tomorrow, it's as a result of that sympathetic nervous system. Because you're either fighting the aspect that you have to deliver. You have to have glucose in the bloodstream. Your breathing has to deliver oxygen to all your hard-working muscles and glands. Your nervous system uses more oxygen and more glucose than any other system in your body. And nervous system thinking, think about it. You're thinking. Are you thinking? You're thinking. Serious amounts of glucose and oxygen being used, and think of how much you've used it over this week trying to get your academic inquiry reported. Okay? So that's sympathetically driven, delivering and sending all of that around the body. But it really comes into play in scenarios where you have to perform. Such as, I'm sure you've all heard of circumstances where mothers have lifted cars off of babies. Or, you've run faster than you ever have. Or perhaps you've managed to scale a mountain but you didn't even think you could climb a hill. Or whatever it might be. Sometimes, in certain situations where you have to perform life or death type scenario is where sympathetic comes into play. So if you saw a lion standing out on the street, some of you might decide to wrestle the lion, so that would be the fight aspect, and some of you might decide to flight, so run away. I'm hoping you run away, no one should take on the lion. Luckily we live in New Zealand, so there won't be a lion on the street, but you never know. Actually, there was a leopard that was walking around England a little while ago. Did you guys see that? I can't remember where it was. Anyway, so fight or flight. What are the responses do you think that would happen in a crisis situation? If Your heart rate would speed up. What else? Adrenaline would be released, and that's the major. So adrenaline and cortisol would stimulate heart rate to increase. What else? We'd start sweating, definitely. What else? Are you going to hold your breath? Breathing, definitely. What else?
Would you get lactic acid buildup?
Depending on what you were doing, yes. So like if you were having to run a long way or, yeah, definitely.
But doesn't it start producing when your heart rate increases though?
No,
Not
lactic
straight
acid,
away.
it's when you're not getting enough oxygen on board.
Okay.
Yeah. So if you increase your breathing, then not essentially straight away. But if you were sprinting or doing anything power-based.
Anything with anaerobic
Yeah,
respiration.
exactly. Okay, and glucose. You guys, your body has an amazing ability to flood the blood with glucose. Where does glucose come from if you're not eating? Where's it stored?
Insulin.
Glycogen. Where's it stored? Where's that? Liver. Good. It's also stored in other places. Where else? Now, just the ability to be able to do this, you know you've got glucose stored there because you need it when you haven't been eating. Eating. Because of the lion. Yeah. Okay, so you have glucose that floods your system as a result of the sympathetic nervous system, so you can run the distance or climb that mountain or lift the car or whatever it might be. Okay, but the problem being if you're too sympathetically driven, and we are all too sympathetically driven because we live in this environment. I mean, who goes to bed before 10 o'clock? Good. Okay, don't change that. Anyone else go to bed before 10 o'clock? 10:30, okay, not bad. Unfortunately, because of being a student, you probably have jobs or try and have to help out with other things. Life pushes that bedtime to 11, to 12, to 1, next 2. Exactly. And so consequently, you're not allowing your body to repair, you're not allowing yourself to switch out of that sympathetic stage and move into the parasympathetic stage. So we need balance, okay? And the two nervous systems play a major part in our lives and control those aspects. However, sometimes we're calling on the sympathetic side a bit too much as a result of caffeine. Okay, so turn in those workbooks or back to our chemistry pages, which is page 65. Yes.
No chemistry.
Oh, sorry, I never gave you that label. So the lower part, apologies for that. Having a blonde day. Oh, that's every day, yeah. Okay, it's your peripheral. That says peripheral nervous system. So essentially what that means, you think about it, brain, spinal cord, central nervous system, and it sends the impulse to your periphery. We talk about periphery being skin or periphery being muscles. Periphery is away from the midline, away from the central point. Brain, spinal cord being central. Peripheral nervous system is those nerves carrying the impulses to the autonomic nervous system to make your heart beat. Autonomic nervous system make you breathe. Autonomic nervous system make your glands release, etc.
So, the nerve has strength, which is peripheral, central.
So essentially your nerves, like if you look at
Like-
so you got your brain and spinal cord.
Like a
and
branch.
all of those- yeah. So that picture on your nervous system is quite helpful because you can see the brain and spinal cord and then the nerves going out. Right, page 65 please people. 65. Now before I forget, your quiz number 2 is due next week. We will be marking it first thing. Okay, so for those of you, I know certain people were trying to finish off last minute things. However, if you're not in class, you don't get the mark. And send nudge nudge to the people who were late. Not looking at anyone in particular. Okay, so who snuck in late? Is Brett? No, Brett. No. Jody. I think she's sick. Faith. Helen.
Are you sure you want to library, bro?
What? Honey? Oh, it's so close. I tried rolling my eyes and didn't pronounce that. Cynthia.
Halfway through.
And Malaz. Nat? Nat? Cynthia here? And Walter's here. Great. Okay, so chemistry. We touched on this aspect last week, the fact that science involves more than just gaining of knowledge, it's the systematic or systemic and organized inquiry into the natural world and its phenomena. So science is awesome, so we're going to break it apart. Did you have a question or are you stretching? Okay, so on page 65 in your workbooks, 65, now some of the aspects of matter you've already added to. So the fact that matter occupies space and it has mass, you should have already written that down. You also need to write that it is usually seen, smelt or felt, and it's a solid, a liquid or a gas. So I don't think you've got that aspect on your little matter column, so make sure you add that matter is a solid, a liquid or a gas. So essentially matter is everything around us. It is the table you're working on, it is you, it is the water you're drinking, the air that you can feel, the air around you, the air you're breathing, it is everything, okay? And you can change matter both physically and chemically. So for instance, if you were to bring a big axe into class and chopped up your desk, you would be changing the structure physically, because essentially we could get some super glue and glue it back together. Not very well, but you've only changed the structure physically. In contrast to if you brought in some matches and burned the desk, it turns it into ash, so then it would be chemically changed, because you couldn't really glue ash back together to make a desk. Likewise, physical change, ice melts. So take ice, let it melt. The structural composition of the water molecules is the same in ice as it is in water. Okay, so it hasn't really changed, it's just expanded. In contrast to chemically digesting food, eat an apple, it doesn't come out looking like an apple. Okay, so it's chemically changed. Right. So you should have those aspects of matter. Now, when we look at water, now we're going to be dealing with water a lot today, you guys. We're going to be looking at the molecule structure, we're going to be looking at the bonds formed from one molecule to another, and we're going to be trying to understand what water is. So, what is the chemical formula for water?
H2O.
Yeah. So, this is water over here. If you have a look, we've got H2 means 2 hydrogen and 1 oxygen. Good. So these little molecules are all individual water molecules. Okay. I won't draw all of them, that's an O. Okay, so that's one water molecule, that's one water molecule, that's one water molecule, and it all sits in a glass and it has bonds that form from one molecule to another, and that's why when you look at water in a glass, it doesn't look like separate molecules, it just looks like water. Exactly. Okay. Now, when we look at water, we're also going to look at what sort of bond keeps the hydrogen and oxygen together, and why the hydrogen stays with the oxygen, okay, whether it's stable or unstable. We're also going to look at how it changes its state. So when you look at this one here, this is ice. So the water molecules are still exactly the same. So we've still got 1 oxygen, 2 hydrogen, 1 oxygen, 2 hydrogen, 1 oxygen, 2 hydrogen. But they form these little bridges that create space between them. Okay, and that's ice. And then we're going to look at water as a gas. So when water is heated, how it turns into a gas or steam and how it moves around in the beaker as such. Okay, so water is really interesting, how it interacts in the body, on the environment, etc. Now, next part, so next block down we have energy. So apologies if you can't fit this all in, you are going to need it, so add it to that box, or on page 70 if you have additional space to write notes, or page 64 if you haven't filled that all already. So, energy is the capacity to do work. So essentially, put matter in motion. If you were to put your hands on the desk, I've already said the desk is matter, shove it, energy needed to do it. Okay? So energy is the capacity to do work. Energy exists as both kinetic and potential. So kinetic energy is the actual doing part. So as it says there, energy in action is kinetic energy. So if you were to shove your desk, that's kinetic energy. Potential, in contrast, is stored energy. Okay. So if I say, everyone freeze, freeze, like freeze, freeze, freeze. That's potential energy. You so want to continue writing. Where's the 10-year-old? You so want to keep writing, but you're frozen. You have the potential to keep writing, but you weren't. That's stored energy. It's like when your parents say, oh, you have the potential to be great. You're not quite great yet, but you have the potential to be great. Okay, so it's potential means stored, and these are words you know, but we're just putting them into context. Okay, so potential energy is stored energy in contrast to kinetic energy, which is the doing part. Okay, and we're going to look at the different types of energy. So when it says that when energy is released, it becomes kinetic energy, allowing it to do work. So let's look at the different types. You all got that? Yeah? Good? Okay. So we've got different forms. So we're going to look at chemical, electrical, mechanical, and radiant. So you're going to need to add this to a spare piece of refill or on page 17. Chemical energy is when ATP is produced or broken down. So essentially it is when we chew food, eat food, swallow food, and that helps to produce our energy reserves. Or when we go to make ATP, which is energy. The making of energy burns energy, which then creates energy. In your workbooks on page 70, you also have an additional page. Now, electrical energy, as I said, nervous system. The relaying of, don't worry about that, the relaying of nerves sending electrical impulses from one neuron to a muscle, from one neuron to another neuron, from the brain and spinal cord, the central nervous system, to where it needs to go. Electrical stimulation. And it's pretty cool because we're going to look at how ions convey electrical currents as well, and what an ion is. Mechanical energy is muscles pulling on bones. Simple as that. And then we've got radiant energy, so energy that travels in waves, such as from the sun. So the creation of vitamin D in our body. So when you think about the different types of energy, you have the perception, you have the knowledge of them already, so now it's just putting it into context. Not bring your books in. They can catch up.
I've done most of this in basics and things.
So take down what you need to add to your slides. Okay, and then when we convert this energy, so energy conversion, whether it be mechanical, whether it be chemical, whether it be electrical, we are able to convert the energy into heat. In most cases, the energy supply is constant. However, at times, some energy is lost in the conversion process. So, as it says there, in most cases, energy is easily converted. During an energy conversion, some energy is always lost to heat. All energy conversions in the body give off heat. In turn, the heat helps us maintain our body temperature. For instance, mechanical energy, shivering. What does that create?
Kinetic energy.
Which is heat. Good. So we shiver to warm ourselves up. Yeah.
So how's the the static energy happen?
So that would be exothermic.
Oh,
That's because of electrical currents outside the body. So, like if you walk with socks, doing that, because of the negative ions, in contrast to your body being positively charged, creates a shock. It's kind of you transferring the electricity into the carpet or something like that. I'm not completely up to date with it, but okay, we get a video. We're all writing that down. It's just a bit of fun. So, meet a rhino. And mute. So, this rhino here, based on his height above the ground, the rhino possesses gravitational potential energy. Okay, so what's gravity?
Force.
Why did you
Good. Force pulling us towards Earth. Potential? Stored. Lovely. So he's standing on top of a building. Now this is something we see every day, isn't it? Okay, so he has that stored gravitational energy. He jumps. During the fall, most of the potential energy converted to kinetic and a small amount to heat. The rhino moves through the air, generating friction. So, upon impact, the kinetic is converted to heat, and some chemical bonds are broken in the pavement, plus sound energy. The gravitational potential energy is converted into a range of energy forms, but overall, the total energy remains constant. So, essentially, what it's saying is conversion takes place. So, potential energy converted to kinetic energy because it jumps off the building. So that generates friction as he moves through the air, then hits the pavement, breaks the chemical bonds of the pavement, still physically the same. However, that impact then, as it says, gravitational potential energy converted to a range of different energy forms. However, it's still constant, even though it's converted to these different types. Some heat is lost, some energy is lost to the heat, but just for that. Right. Okay. So, sorry, now we've got sound effects. So sound effects are on as long as volume's on. Apologies. Okay. Now looking at elements. Now, for those of you who wrote this down last week, apologies. As of this year, 2015, we now have recognized 118 elements on the periodic table. And last year's, 2014, this year's 215, 2013 textbook, it was at 112. Okay, so there were additional elements that were being reviewed, but now they've been recognized. So we're now at 180. So all matter is composed of elements. As we know, an element is a structure that cannot be broken down into simpler substances as well. So we've got matter, and elements make up matter. Okay. So now we know we've got main elements and trace elements, which we've touched on. So elements can vary between carbon, hydrogen, oxygen, nitrogen. Make sure you change in your workbooks, if you haven't already, that it's 118, not 112. So 92 occur in nature and 26 artificially. Don't worry about this part because we're going to go through our main and our trace. However, it's important to know that there are 20 other trace elements in the body that play minor roles in the running of day-to-day functions. And as we know, the periodic table lists all elements and explains the properties of each. Okay. So, our elements. Don't need to write down the main and the trace because we should go through them. You've all got the main and the trace written down though from last week? Okay. So, our main elements. And remember exactly, HUNC. What does HUNC stand for? Hydrogen. Beautiful. Okay, so we've got our functions. You should have these written up already. Guys, double check. Apparently some of the other classes told me that they had written hydrogen for nitrogen and nitrogen for hydrogen. My order was different to your order in your workbooks. So double check you've got it in the right order. So essentially nitrogen should say something along the lines of essential component of protein and genetic material. Okay, and hydrogen is all about the pH balance, so component of organic molecules and pH balance. So if you flipped it, flip it back. Apologies, my order was different to your order. So draw a circle and an arrow. Sorry, I didn't realize. Okay, so carbon, as it says there, component of organic molecules. Primary component of all organic molecules. Carbs, fats, proteins, molecules. Okay, carbs, fats, proteins. Oxygen, major component of energy. Oxygen, all about energy, both organic and inorganic components, as well as being necessary for energy for the ATP production. Got it all right. And then hydrogen, pH balance. Okay, so double check those. If you need to, put in an arrow. Okay, so we've got HUNC. Now what was the little acronym that I said for our trace elements? PIX or SPIC? Whichever you prefer. So PIX stands for? Potassium, iron, calcium. Lovely. What's wrong? Did you get this one wrong too?
Potassium's okay, but you know. You don't want to write the fact that do you? It's just not there. No. Oh yeah, okay.
Yeah, so put a line through hydrogen there. That's right. Nitrogen. Yes, put a, no, so that's hydrogen.
Vecna.
Yes, so that's right.
Vecna.
Yes, so that's right. Just those two. Yeah. So this one is a little line through hydrogen.
Fenica. You studied physics?
Right.
No, I did it.
So, need to remember the functions of our trace elements as well. Okay, so iron, component of hemoglobin, all about transporting oxygen. So if you don't have enough iron in the blood, you're really tired and fatigued and lethargic. It's called anemic. Okay, calcium, bones and teeth, but that's not enough. What else about calcium? Blood clotting, what else? Nerve conduction, what else? Muscle contraction, lovely. Okay, potassium and sodium work together and we'll explain why in a few weeks' time. Necessary for conduction of nerve impulses, as well as muscle contraction, and major positive ion in cells. What's the word for that? Lovely. Intracellular. And then sodium is extracellular. So extracellular means outside. So important in water balance, muscle contractions, nerve impulses, and it's a positive ion in the extracellular fluid. Okay, good. So those are our main and our trace elements. I'm telling you now they will be in your exam, so learn them and learn their functions. That's just a subtle hint, hey? Just subtle. Okay, moving on. So, our atoms. So, as we know, atoms make up elements. So the tiny, tiny parts form together to make elements. So atoms are small, but atoms are made up of even smaller particles. These subatomic particles differ in mass, electrical charge, and position. The fundamental unit of the chemical substance, and atmos means uncuttable. So an atom is the smallest possible particle of an element. It is extremely small. So once you've written that in, wherever you are writing it in, so this part, I want you to turn to page, turn to page 66 and write this part in just in the corner. Okay, so on page 66 you'll see you have structure of an atom. Now, so write in just this part, and then we're going to go through the part that's already in the workbooks. So essentially when we're drawing an atom, it looks something like this. Okay. Now your atom has a nucleus. You guys okay? On page 66, right in this part, page 66, and that would be 65. Okay, so that's the nucleus. And as it says in your workbooks, the nucleus contains protons and neutrons. So in your workbooks on page 66, it says the nucleus and the structure of the atom. Nucleus contains protons and neutrons. Then it says the electrons orbit around the nucleus. So these circles here, those parts there are called orbits. Okay. And on the orbit we have electrons. Now, within the nucleus, so in this part here, we have something that are positive, and they are known as protons. So in your workbook it says within the nucleus we have protons which have a positive charge on page 66. The neutrons have a neutral charge, so no charge. And on the electron orbit we have what's known as electrons that look like this. And they are negative. Okay, so negative charge. So next to, on page 66, you want to write this in. So protons have a positive charge, neutrons have a neutral charge, and electrons have a negative charge. 66. Wrong 66. It is 66. Yeah, I'm saying wrong 66.
Do you write
This
here?
might be different to mine. Yeah.
Yeah.
So
Ah, okay.
protons have a positive charge. Neutrons have a neutral charge. You got it?
Neutral. Or
And
no
electrons have a negative charge. You got it? Yeah, on there.
and negative.
Yep. You got it. So just make sure you write those two parts as well. Then.
Oh, atom.
Yeah, just write it in the corner somewhere. You guys got it?
That's a very sort of open-ended question. It could be anything, you know, very open.
Okay. So,
Like you could have so many answers for that. I just like now to me, let's move on. So, yeah.
let's break that apart further. So when we're looking at an element, so remember atoms, smallest part of the element. Elements work together to create matter. So your desk, the air. For instance, the air, what are we breathing? What's the main thing we're breathing in?
Oxygen.
Oxygen. What's oxygen? What's the O2? Okay, so what does that tell us about oxygen? There's what? When you say O2?
There's two of them.
Good, there's two of them, two atoms of oxygen. Okay, so two atoms of oxygen making the element. So let's look at carbon. This here, and you're going to need to kind of just write in the atomic number somewhere. I want you to have an understanding of the atomic number. Because the atomic number, this number here, so this is carbon on the periodic table. Okay, the atomic number is both the number of electrons equal to the number of protons. And this is very important because you're going to be needing to draw in electrons on atoms. And you need to remember that whatever the proton number is, will always match the electron number. Okay? So atomic number. We're not expecting you to be able to calculate atomic mass or worry about atomic mass, so you can write in the definition of it, however, we won't expect you to do it or figure it out for us. And so each element on the periodic table has a letter. The letter doesn't always match the name of what we're talking about, and this is due to the fact that it's quite often in Latin or Greek, exactly. Such as ferritin, which is iron, so we look at it as Fe, however, iron is my exactly. Okay. So we're going to jump around between understanding how atoms work, how they combine, and how to draw the the electrons onto the orbit for each atom. Okay. So if you've done chemistry before, you guys are probably going to whiz through that. So those of you who have done it before, help those around you. Okay, because some people haven't. Okay.
Help me.
So, atomic structure. So this is just an example of what I've drawn here. Let's look at hydrogen first. So hydrogen is quite cool. Now, quite often you'll see it's drawn like that, or you will have an actual clear-cut nucleus, and then we might see something like that. Now, 1p means there's one proton. What did we say the proton was? Positive, lovely. So it's got one proton here, and if we've got one proton, what does it tell us? One electron. Okay, so this is nice and easy. It's written out for us. So we've got one proton, one electron, hydrogen. Now we've got helium, two protons, 1, 2 electrons, and now we've got 2 neutrons in one as well. Okay, but as we know, the proton number always matches the electron number. At times, however, the neutron number doesn't. So we're going to look at what it's called in a second when the neutron number doesn't. Okay, but we don't deal too much with neutrons at this level. Then we're going to look at lithium, so 3 protons, 1, 2, 3. 4 neutrons, 1, 2, 3, 4. But when there's 3 protons, there's always 3 electrons. Very good. Okay, so when we don't have an even number of neutrons to protons and electrons, it's called an isotope. So don't worry about this part here, that's just a bit of information. You need to write down what an isotope is. So an isotope is a structural variation when the neutron number does not match the proton and the electron. So an isotope is when the neutral number, does not match the proton and the electron. And an example would be hydrogen, as we just saw. Hydrogen, yeah, or uranium. So don't worry about this part, okay? Don't write this down. That's just a bit of information. So all it's saying is the process of atomic decay is sometimes called a radioisotope. Okay, so a radioisotope still has a differing number of neutrons, but what happens is iodine 131 is used to determine the size and shape of the thyroid, the activity of the thyroid gland. It is used to detect thyroid cancer, but at times radioisotopes can harm the body too. For instance, if you inhale particles from decaying radon, it can cause lung cancer. Okay, so at times radioisotopes can be detrimental or beneficial, I suppose. Just copy down that. No, don't worry about radio. Don't need it. That's just information. So just the top part. Isotopes, structural variation, neutron number differs from proton and electron. That's all you need. times atoms combine. So we've mentioned oxygen just before, which is O2, okay? And look, here it is here. So oxygen would be called a molecule, because a molecule is when two like atoms combine, okay? So most atoms don't exist in free state. Instead, they combine with other atoms through chemical bonds, forming molecules and compounds. Okay, so they don't exist alone. The atom actually has another atom or different atom that it joins with. Okay, so we've got example, hydrogen, H2, oxygen, O2, nitrogen, N2, and chlorine, Cl2. Now, at times we have when different atoms combine, so that would be called a compound. So nitrogen oxide, nitrogen and oxygen, water. And it's funny because you always talk about a molecule of water, but it's actually a compound of water, or a molecule of a compound of water. And so you've got 2 hydrogen, 1 oxygen, or nitrogen dioxide, 2 oxygen, 1 nitrogen, and carbon dioxide, 2 oxygen, 1 carbon. Okay? So in definition, a molecule, 2 or more like atoms combined. So it becomes the molecule of that element. Okay? A molecule of that element. A compound is 2 or more different atoms combining chemically, becoming a compound molecule. An example is salt. Salt is a compound molecule. And luckily it is able to combine, because otherwise we would be putting sodium, which is a silvery metal, or chlorine gas, which is highly poisonous, on our food.
Put potassium chloride.
Potassium chloride. Okay, so atoms combine, if they're the same, they're molecules, so if they're different, compounds.
Is there a lot of chemistry in the exam?
There generally is an element, there's an element of chemistry in the exam. So it will be like drawing electrons on an atom or explaining different bonds. It is quite simple, the chemistry we do. More focus would be on cells and homeostasis. But there is an element of it. Always. Okay, let's move on. So, right, here's a bit of a challenge. So you have to get your chemist way of thinking on. Okay, if you saw an ice cube sink after it was placed in what you thought was a glass of water, which question should you probably ask? So you're all chemists, okay, so think scientifically. Either A, what kind of liquid was in the glass? B, will the ice melt slower or quicker? C, how fast did the ice cube sink? And D, how soon would the ice cube start to float? What do we reckon? A and B? A or B? Any other viewpoints? E? Okay, A or B? No one else? Okay. Let's check. Not B. Not C. Not D. It's A. So, why? Why should we ask what's in the glass? Yeah.
Ice isn't as dense as water.
It's what, sorry?
It's not as dense as water. It sits on top and floats.
Nice. But what is it more dense?
Pardon?
When is ice more dense than a liquid? That's a good sign. We don't know.
I don't know.
Okay. How many of you have been out recently and your friend said they were drinking water and the ice was sitting at the bottom of the glass?
Okay, so things like when they're different substances. I thought you meant like the same substance at different states.
Okay. Yeah, no, sorry. Vodka, exactly. It would sink. Whiskey, any other neat alcohol for that matter. Not creamy alcohol, so if you have Baileys, it will sit on top. But any neat alcohol, ice is actually denser than the alcohol. So the ice sinks. But in any water state, so if you've got water, if you've got fizzy drink, fizzy drink, juice, you name it, even if you have vodka and juice, or vodka, they're still going to have ice at the top. But if your friend says, yeah, I'm just having water tonight, and that ice is sitting at the glass? Yeah, you might need to tell them to recheck that. Okay, so why? Why does ice float on water but sink in alcohol? So, as you said, ice is what?
Not as dense as water.
Not as dense as water. So if you remember back to those beakers, you know those 3 little beakers we looked at, of water, of ice, and of gas? So the water molecules, they are moving around continuously, forming bonds, breaking bonds, forming bonds, breaking bonds. When they freeze, they create space. So the water molecules don't change, but they create spaces between them. So that space makes them less dense than the water itself. And so hence why it sits on top of water itself. Okay, so it floats. However, when you put it in alcohol, it sinks. So it's actually more dense than the alcohol itself. Okay? So it's quite interesting. And then we've got the next analogy as well.
Is that because ethanol has more electrons and has a bigger plane then?
Yeah. Okay, so stay there. Well done though. Okay, so hot air balloon rises because, so we've got 2 A's. Apologies. A, molecules become lighter when heated. B, or A, molecules are less attracted by gravity when heated. B, molecules become charged and repel each other when heated. Or C, molecules move faster and farther apart when heated. C? Any other views? This side of the class?
Wait, is it meant to be C or D?
Yeah,
It's
correct.
last way.
Go with C.
Oh,
A1 or A2 or B or C. It's like Mary 1 and Mary 2. So now we've got A1 and A2. So we're going C. We all think C? Okay, let's check. Not A. Not A's. Not B. It's C. So once again, thinking back to those beakers. Remember in that beaker where water had turned to steam? There were only 2 little molecules that you could see. So it shows that the molecules were moving faster and further apart as soon as they heated, and hence, hot air balloon left. Okay, so we've answered this one. This is the same scenario as water. Ice cubes float in a glass of water because, as we said, the molecules of ice are arranged in an orderly way so that there's unusually a large amount of empty space between the cubes. It's kind of like who's been to Tarpo recently, picked up a rock to skim it along Lake Tarpo, and then it turns out to be pumice. Floats. Yeah, it always surprises me because it looks like a rock. Well, it doesn't feel like a rock because it is lighter, but it looks like a rock, but it's actually pumice and it floats away. So cool. Okay. Right. Which symbolizes a molecule of a compound. So what did we say a compound was? 2 different atoms. Okay, so what do we reckon? Salt. Which is? Okay, so for those of you who didn't realize, sodium is Na. Okay, so sodium chloride, NaCl. Well done. Okay, what about this one? An atom is to an element as a molecule is to a? Nice. You guys have skills. Compound. What? One last one and then we'll have a break. So, all plant and animal life on Earth contains what element?
Carbon.
Good stuff. Okay, so it is now 2 o'clock. Not 2:30, 2:15, but you have to do page 67 as well. Okay, so hence making it, it's a little bit, okay, so I'll say 2:20 and then come back at 2:30. But you have to have done page 67. So either do page 67 now and go for a break. If
Yes,
not,
please.
go for a break and then do it.
Electrical
And if you've done it
icon or-
already, you get a longer break.
Following the words, okay?
Clearly, Henry.
Unless charged atom or group of atoms.
Yes, we've got time for this. The atoms family story. This is very important. You need to concentrate.
So are we writing it down?
No, you don't need to write it down. Okay, so in the centre of Matterville is a place called the Nucleus Arcade. So this is the Nucleus Arcade, that part there, where 2 members of the Atoms family like to hang. Perky Patty Proton, that guy there, it, like her sisters, is quite large with a huge smile and eyes that sparkle. Signs. Patty is always happy and has a very positive personality. Nerdy Nelda Neutron is large like Patty, but she has a boring flat mouth and eyes with zero expression. Zero. Her family is very apathetic and neutral about everything. Patty, Nelda, and his sister spend all the time in the Nucleus Arcade. Around the Nucleus Arcade you find a series of roadways. So it's orbits are the roadways that are used by another member of the Atoms family, enraged Elliot Electron. Oh, pardon me. Elliot races madly around the arcade on his bright red chrome-plated Harley Davidson. He rides so fast that no one can be sure where he is at any time. Elliot is much smaller than Patty and Nelda, and he's always angry because these bigger relatives will not let him in the arcade. He has a frown on his face, eyes that are squinted with anger, and a very negative attitude. Right. So, now we need to understand the rule of eights is what it's called. So I would like you to look on page 66 of your workbooks where it says electrons. Okay, so we're talking about enraged Elliot Electron, who has a very negative attitude. And what did we say? He's only allowed on these roadways on his bright red chrome Davidson motorbike. Glasses. There we go. Okay, so the second let me show you. There's our Nucleus Arcade that the protons and the neutrons live in. Then our second energy street, and if you look in your workbooks, you'll see it says shell 1, closest to the nucleus, has a maximum of 2 electrons. So shell 1 is this one here, and it can only ever take 2 Elliot electrons. It's just a rule, okay? And that's the end. The 2 electrons are allowed to go there, and that is all. And we always fill from this shell first. So if you have to draw in electrons, you fill them in on this shell first, and then we move out. And that one can only have 2. Because remember, Elliot Electron wants to get in the Nucleus Arcade, but he's not allowed. So he has to go on that one first. They're the best seats in the house. They like the front row seats, so that's why that one fills first. Then the next shell, bless you, can only hold 8. Okay, so as it says in your workbooks, shell 2 holds a maximum of 8 electrons, and then shell 3 a maximum of 18. Now above that little analogy in your workbooks, I want you to write in that it's called the rule of 8s. So in your workbook, just above the rule of 8, where it says shell 1 holds 2, 2 holds 8, 8 holds 18. So just here, write in that is the rule of 8s.
True.
Yeah, so just write in that's called the rule of 8s. So that's the electron
Why does it call the rule of 8?
You and him together. No, it's not there. So you're going to be there. Oh, pages.
Why do you
Go too far
call
this way.
the rule of 8?
Because essentially it goes up to 8. Okay, so even though the third ring takes 18, it would be stable at 8 as well. Okay, but it's kind of wonky because the first orbit is 2, the second one is 8, and that's the only one that's 8. Although the third one can be 8, but it does go up to 18, and likewise subsequent ones. Okay, so the whole aim of this is to make atoms stable. Okay, and atoms have the ability to share electrons or steal electrons from other atoms to be stable. Because if they don't follow this rule of 8, they are what's known as reactive. And so we'll get a definition for that in a second. So, on that note, I want you to think about the following. So the morale of Matterville is stable as long as each negative electron brother is balanced by one positive proton sister. The number of residents in Matterville depends on the proton and neutron families. Now, what would happen to the morale in Matterville if an Elliot electron was kidnapped? Okay, so when electrons move from one atom to another, so when they get stolen or kidnapped, you need to think of the electron as being a really, really grumpy person. Okay, so a way of thinking this, say for instance I came into the class and I was really moody and I was yelling at all of you and telling you you're all idiots and stamping my feet and throwing things at you, how are you going to feel? What did they say? No good. I'm just so excited. I was like, seriously? Okay. So, you would feel negative. If I was really, really, really negative and grumpy and growly, and I was relaying that on all of you, you would feel more negative. You would feel negative. But if you kick me out the class, so grumpy as me is leaving, negative me is leaving, you would feel positive. You could celebrate. Okay, so same applies with electrons. If Elliot electron is kidnapped, stolen, kicked out of the class, we are all going to be positive because we've got rid of the grumpy bug. But then, in contrast, if we gained an electron, so we get another electron, so electron comes into the class, he's grumping, he's growling, he's yelling at all of you, what are you going to feel? Stink. Negative. Okay. So if we gain electrons, the atom or the class becomes negative. If we get rid of electrons, we become positive. Okay, now when we start doing this, when we're looking at drawing electrons, getting rid of electrons or gaining electrons, you need to think of it from this perspective. Okay, because quite often people will think of it like from a money perspective. Give me money, yay, lose money. But we want to lose, like if we lose electrons, yay, gain electrons. Because gaining electrons makes us grumpy. Gaining electrons make us negative. So think of the gaining as a grumpy person making the whole morale negative. But getting rid of electrons will feel better because grumpy as electron has gone. Does that make sense? So think of it as a mood thing rather than as a gaining thing. Okay, and I'll explain why in a second. But first you get a fun song. Yes, this is highly educational and you all have to memorize for homework.
What?
I can't believe you did this. I'm going out. No, love, you can't. You're too upset.
You can't drive like this.
Get the book at asapscience.com.
And now, ASAP Science presents the elements of the periodic table.
Oh
There's
no.
hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, and oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, and argon, and
potassium,
calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, no gas is stable. Halogens and alkali react aggressively. Each period will see new outer shell electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel coins you get. Copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine. Then we'll electron helps light up your room. Rubidium and strontium, then yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits. Well, lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, chromium, erbium, thulium, terbium, lutetium. Hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, flavium, and lead the biscuit for your tummy, polonium, astatine would not be yummy, radar, francium will last a little time, radium, then actinides at 89. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shell electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, uranium, curium, berkelium, californium, titanium, fermium, indolenium, nobelium, lawrencium, rutherfordium, wm, sprigium, boreum, mesium, meitnerium, obsidian, marcanium, copernicium, unnatrium, flerovium, unpentium, livermorium, unseptium, unoctium, and then we're done.
What?
Like the song? Be sure to check it out on iTunes and Bandcamp. Links are in the description. And if you think you have what it takes to know.
What?
Okay, so Harry Potter, what's his name?
Daniel something.
He sang it on
Brang.
Yeah, Ben.
not quite that version. Actually. He sang the Pirates of the Penzance version. Anyone know that one? Modern Major General. Anyway. So he's very talented. Here we go. Okay, so atoms, smallest unit of elements. Elements, as we know, main trace, complex, combined to form matter. So, four main elements, what are they? Carbon. This side of the class? Hydrogen. Oxygen. Nitrogen. Well done, next side of the class. Wake up, you lot. Higgs, this side of the class. So our trace elements. Potassium, iron, okay, well done. This side.
Calcium.
Calcium, sodium. Nice. Okay, four main elements, four trace elements. Now, if you got asked in the exam, what is organic? What would you say? Or what is the difference between organic and inorganic?
Naturally occurring and synthesized things. Organic being occurs naturally,
Good.
and inorganic means you have to synthesize it using
Okay.
collections of other things.
And organic contains?
Carbon.
Perfect. Great answer. Okay, so if you haven't already, let's write this down. Organic means it contains carbon, naturally occurring. An example could be carbohydrates, proteins, and fat. And here's an example of glucose molecule, C6H12O6. Inorganic means it lacks carbon, so it's complete. Just reversing what we're saying, very easy, straightforward. An example would be water. Now we did touch on it last week, that organic contains carbon. So when we wrote the main element, we said carbon is a component of the. It was in your quiz, yeah. Oh, the last quiz. First quiz. It's right there, sorry, I went back to that. You see, these quizzes are helpful. That's your first answer. Thank you for that. Make sure you write it down. No, not in your quiz, in your notes. Okay, moving on. So, we don't need to do that. Now, chemical reactions. Okay, so when, as we said, atoms are, so atmos, what did we say atmos means? Uncut. Okay, so the basic unit. However, when you break the bonds of an atom, we get a tremendous amount of energy, like the atomic bomb. Okay, so breaking atoms releases energy. Okay, so we couldn't cut them by ordinary means. When you bring in chemical reactions, we can break the bonds, releasing that energy. And so consequently, atoms in molecules are united by these chemical bonds, which is controlled energy, but breaking the bonds releases the energy. So they dissociate from one atom when a chemical bond is broken. So we're going to look at bonds. Okay. So when we're talking about bonds, now you guys, some of this information you have in your workbook, so don't frantically write, just have a read before we go on, and I'll tell you what's in your workbooks and what's not. So electrons occupy energy levels called electron shells. So in your workbooks on page 66, we have that part on electrons. As it says, electrons orbit the nucleus. Oh, look at that. You're the first person to notice that. Well done. Electrons, put in your R. That's been there for quite a few semesters as well. Well done. So electrons, meant to be electrons, orbit the nucleus. Okay, so as we said, the nucleus arcade you know, where proton, Patty Proton and, what was the name, Nerdy Neutron live. So electrons sit on the orbit and they sit on the orbit shells, the energy levels, and orbit the nucleus. Now, as we said, electrons closest to the nucleus are most strongly attracted. So these are the front row seats. Those are the ones that are going to fill first. And how many did we say could go on the first row? Two. Very good. Okay. So only 2 electrons can go on the first orbit. Now, if there's only one orbit, I'm just going to rub that out. If there's only one orbit, we just have 2, and that atom would be called stable. Now, if there's only one, like hydrogen, we're going to see a type of bond occur. And it is this outer orbit that is the most reactive orbit. So there could be 1 orbit, there could be 2, there could be 3, depending on how many electrons they are. Okay, and as it says here, bonding involves interactions between electrons in the outer shell. So if it's hydrogen, which is 1p, so 1 proton, so 1 proton means 1 electron. So consequently, the outermost shell, known as the valence, is the most reactive part of the atom. So it is going to need another electron for that shell to be stable. Do you understand that? Because how many electrons in the first shell? 2. But there's only 1. So it needs to find a friend. Count. Each shell, as it says, has distinct properties. The rule of 8. So we've already established that we have the rule of 8 in our workbook. So shell 1, 2. Shell 2, how many? 8. Shell 3? 18. Up to 18. Good. So let's have a look. There you go. Rule of 8 is also known as the octet rule. The first shell, so atoms are considered stable when their outermost orbit has 8 electrons. Atoms will gain, lose, or share electrons to complete the outermost orbit. So as I said, the first orbit fills first, so let's ditch that. So if we have 2 electrons there and then there's another electron, then we'd move on to the next orbit, sorry. Okay, so we always start on the innermost orbit working out. So for instance, if it was 6p, we'd do 2, and then 3, 4, and you've got to use your math skills here because we've got 2 already, so how many more to make 6? Another 2, so 1, 2, 3, 4, 5, 6. Okay? So the exception to the rule is the first shell, which is called the duet rule because it only holds 2. Okay. Now, an atom is inert or stable if it has followed that rule of 8 properly. Okay, so if it has 2 and then 8, or 2, 8, 18, whatever it might be, if it has followed that rule, it is stable. So you need to write down what the definition of an inert element is. So write this down somewhere. An inert element is when the atom is stable. Okay, so when the valence shell is complete. So whether it's the first or the second, or the third, or the fourth, or the fifth. So the inert shell is complete. And complete being the rule of 8. Okay, so in contrast, it is reactive if this rule of 8 isn't applied. Okay, like hydrogen, for instance. So, inert elements, helium. 2 protons, 2 electrons. First shell, 2 electrons, so we're good, so it's stable. This one, neon, and it says 10 protons, 10 electrons. So we draw them in. We've got 2 on the first orbit, then 1, 2, 3, 4, 5, 6, 7, 8. How many have to be on the second orbit? 8. So, stable. Okay, stable or inert. In contrast, reactive elements. So when the valence shell is not full, it's unstable. Okay, and we're going to be dealing with reactive elements a fair bit because you're going to have to learn how to draw in the electrons on reactive elements because bonds form as a result of reactive elements. So the valence shell is not full or unstable. They tend to gain, lose, or share electrons, and this allows for bond formation, which produces a stable valence. So it's all about the stability and stealing, sharing, borrowing an electron to complete that outer shell. Okay, so examples would be hydrogen, as I said. There's only one electron per shell. How many do we need?
2.
2. Good. Carbon has 6 electrons. So 6 means there's 2 in the first orbit, but only 4 in the second orbit. So not sufficient. So reactive. Okay. Oxygen, it says there are 8 electrons, but don't forget to always fill the first orbit first. So hence making 2 in the first orbit, so that means there's only 6 for the second orbit. And there need to be how many in the second orbit? 8, exactly, so not stable. Sorry, I'm not blocking. And likewise, sodium, as it says there are 11 electrons. So that's 2 in the first orbit, 8 in the second orbit, so 8 plus 2 is 10. And then in the third orbit, there's only 1, so definitely not stable. Okay, so it's those math skills, huh? You've just got to start first one, then add 8, and then add whatever the number might be. Yeah, and it sounds quite straightforward, but it's important to remember where to fill in the electrons. Make sure you go on the first orbit first, and then go for the 8 in the second orbit, and kind of make sure you're not jumping orbits as well when you're filling in the electrons, because it's easy to move on to the third or something like that. We're going to have heaps of practice though, don't worry. Okay, have you all written that down? Mm-hmm. Okay, so let's practice. Right. I'll have it then. What? Okay, listen on the aisle you get picked on. Draw in electrons. Draw in electrons. So pick one of them. We'll do left side of the class first. So pick one, and it says the protons and you gotta be quick to do this one. Good work, Johnny. Well done. Okay, so 1 electron or 11 electrons. 6, that's it. You're not allowed. That's it. Nice. Good job. Just like that, well done. I was just guessing it. Well, you guessed well. Beautiful. Spiky electrons, thank you. Okay, so let's check. 1 electron, 1 proton, 1 electron. Beautiful, well done. 6 protons, 6 electrons. So 2 in the first orbit, then 1, 2, 3, 4, plus the 2, 6. Very well done. Next one, we've got 8 electrons we need to draw in. So 2 in the first orbit, then 1, 2, 3, 4, 5, 6, plus the 2, 8. Well done. And so can you see how adding, making sure we're balancing it out as you're going? Okay, next one, we've got 11. So 2 in the first orbit, then 1, 2, 3, 4, 5, 6, 7, 8 in the second orbit, and the 2 is 10, plus 1, 11. Great job. And that's all it is. Okay? Yeah. This one? Yeah? So you see how it's 11. So you always fill from the inside first. So the first orbit can only take 2. Okay, so 2 there. Then you've got to fill in the next orbit, which can take 8. So 8 plus 2 is 10. And then because it has to be 11, then you would go to the next orbit and put 1 for the next one. Okay. All of these atoms are reactive. Reactive means?
They don't have
Unstable, they don't have a complete valence. Good. Okay, so they have to borrow, steal electrons to complete these shells. Okay, so if you just got asked this in an exam question to fill in the electrons, that's all you would do. Okay, but now we're going to look at these atoms and what they do as a result of being reactive, as a result of this place. For instance, sodium. Okay, we're going to look at that quite closely. So, well done, you guys. Okay, so now we have all three bonds outlined in your workbook already. So if you turn over the page, we need to go through those answers as well. If you turn over the page onto page 68, it says the chemical bonds. Atoms prefer to have a complete valence, so they bond. Okay, so bonds occur when there is not a full valence, as we said. A molecule shape determines what other molecules it can interact with. So we've got three types of bonds we're going to look at. So first ionic, then covalent, and then hydrogen. So first and foremost, ionic bonds. Now you have some of this information in your workbooks already. Okay, so electrons are completely, in your workbooks it asks for electrons are completely transferred. Good. From one atom to another. So electrons, the negative electrons, are completely transferred from one atom to another. Now, an atom that gains an electron is called an anion. Or an anion. Now, if you think of that word, if you look at it, it looks a bit like this word.
Onion.
Does a bit, doesn't it?
Yeah.
And what do onions do?
Make
They make you cry. Exactly. And what did I say if we gain extra electrons? We get sad. So onions, anion, and ion make you cry. Negative. Okay? So that we gain extra electrons, that would be in a more negative environment. In contrast to atoms that lose electrons. Good. Sorry, I should have drawn a line through that. Cation.
Okay.
Or cation. And kitty cats make you happy, so positive. Okay. You have this in your workbook. So have a look. It says when atoms gain, it's okay. When atoms gain an electron, did you have to fill in the word? Yes, you did. You have to fill in the word. It becomes an anion or an anion, because we're going to look at what an ion is, and an ion is created as a result of an ionic bond. Okay, so what are we doing first? When we when we gain electrons, we become an anion, and when we lose electrons, we become a cation. Okay, so think of always positive effect of getting rid of, you know how you become positive because you're getting rid of grumpy bum electron, but you become negative because you're getting more grumpy bum electrons into the classroom. Does that help with that sort of understanding? If you're thinking of it from a mood perspective rather than a thing perspective. Okay, so either donate or accept electrons. So an ionic bond forms when electrons are completely transferred, as I said. Now, if you have a look at in your workbooks, you have sodium chloride, okay, table salt. Now, sodium chloride, as you can see, we've got the sodium atom and the chlorine atom. So that means on sodium, there are 11 electrons on the sodium. Hey, you guys listen up. On the sodium atom, there are 11 electrons. On the chlorine atom, there are 17 electrons. And then this ionic bond occurs. Now, the ionic bond is the strongest of the three bonds that we're going to look at. So the bond occurs, and then all of a sudden, do you see how on the next picture, when the ionic bond has occurred, it says that Na is positive, there's a plus sign above it, and there are only, if you count the electrons, 10 electrons on the sodium, because one electron has completely transferred over, turning chlorine atom into chloride, and now it has 18 electrons. You see that?
So you stole from.
It's stolen, exactly. Completely transferred it from sodium to chloride.
So the name changes.
Yeah, so chloride would be, not always, but In that sense it does, yeah.
Why would it transfer?
Because it became, so
So
it
how do you
transferred
know
because
there's
it
18
wasn't stable.
Also, it's
It made itself
You
stable
don't
as a
know, it
result.
doesn't change.
The balance was incomplete, so it was reactive. It transfers it over, so it becomes stable, and it completes the valence shell, but then they bond it together. Hence it takes off.
So does that happen all the time if it's stable?
Yeah. So if the valence shell of any atom is incomplete, it's going to look for other atoms that it can bond with to complete it.
Oh, yeah.
Yeah.
And can they only bond with other incomplete?
Sorry?
Can they only bond with other incomplete?
Exactly. Yeah. So if an atom is complete, if the valence shell is complete, it's one bond. It won't steal something from a completed valence. Yeah. Okay. So here's an example. See, oh sorry, this is just our cat. Oh, and that's another example, you guys. Look here. There's a positive sign in the cation when you write it down. See? C-A-T-I-O-N. Positive. So that means we've gotten rid of the electron. Electron's gone. Okay.
There's a line through the A, which is minus.
Right. Look at these two elements. Let's get our electrons up. Okay. So on the first orbit, 2 electrons. On the second orbit, only 1 electron. Okay. Is this one stable?
No.
No. No. Because there's only 1 electron in the second orbit. Okay. What about this one? So there's 2 electrons. First orbit, check. Now second orbit, we've got 1, 2, 3, 4, 5, 6, 7. Stable? No. So both of them are not stable. So consequently, in order to complete that valence, we're going to have a bit of stealing going on. So have a watch. So you see, electrons moving around quickly, and then we have an ionic bond occurring, and no electron in outer orbit, hence the positive symbol, and 1. So what is plus 1? Now, thinking from a mathematical point of view, it's not going to work.
Oh.
Because has it gained an electron?
No,
No.
it has one
No.
more proton than it does electron.
It's what,
It's
sorry?
got one more proton than it does electron.
It does. Okay, but don't go.
Oh, okay.
So even though, yes, okay, I will just start with the electron. The electron has gone away, making it
Positive.
No,
Oh,
the
no,
electron's
no.
gone. Kick out grumpy bum
Positive.
electron. Are we?
Yeah.
Positive. Okay. So it's not about gaining stuff. Plus 1 doesn't mean we're gaining stuff. It means then that the atom has become positive because it got rid of the electron. Okay. So positive, and how many electrons went?
1.
1. So if that said plus 2, how many electrons would have gone?
2.
Exactly. So that's what that number says. Okay. So which is this? Anion or cation?
And cation.
Okay.
Cation.
Good. Cation. There's a plus. And there's a plus in cation. Plus, cation, positive. This one, in contrast, I can't count them because they're going round and round and round.
Well, it'll be 10.
Is now stable because the ionic bond has occurred. And it says -1. So that means what? Gained, even though it's negative, it's gained a negative. So it gained an electron, and we've gained 1. So as it says, the attraction between the cation and anion, or cation and anion, forms the ionic bond. Now, if you haven't written it and write it in, that the ionic bond is the strongest of the 3 bonds, or the strongest bond. Okay, because we're going to look at the weakest bond in a minute.
About DNA.
And the important part to remember with an ionic bond is it's the complete transfer of an electron. Okay, so ionic bond completely transfers or kicks out or moves an electron.
What?
Right.
Ion bond.
Now, okay, so sodium chloride, another example, just a bit of a picture. Sodium and chloride have an ionic bond occurring because sodium sends 1 electron to the chlorine, making it chloride, so it becomes more negative, and sodium becomes positive. So if you see sodium written out generally, it will be Na plus and Cl minus. Okay, and that means Chloride has gained an electron, sodium has lost it. Okay? And sodium, when we look at it within the body, you know how we said sodium in your trace elements, was it intracellular or extracellular? Extracellular. Okay, so its positive effect pulls potassium out of the cell, and we'll talk about that next week. So we'll look at sodium next week and its effects on the body as well, because next week's is cells. Right, covalent bonds. Now the next one down, you'll see you have covalent bonds, and when we say covalent, it's the same as company or collaborate. It means sharing. Sharing is caring. Okay, so atoms become stable through shared electrons. So no longer completely transferring electrons, electrons are now shared. Sharing of electron pairs enables each atom to complete its valence. So hydrogen is an example of this. As we know, H2 or O2, all of those share electrons. Okay, as you can see, look at hydrogen. So we know hydrogen only has one electron. When it's shared, we have two. And the outer valence, well, the first valence has to have how many electrons? The first shell? Two. Okay, so hydrogen is reactive until you have another hydrogen atom with it, forming a covalent bond, and then those two little electrons will race around both of them. So it looks like this. Okay, so we've got, oops, and these electrons will whiz around both hydrogen atoms, okay, making that both atoms stable through a covalent bond. Another example. There you go. See? Both stable. They covalently bond. Now in your workbooks you'll see you have hydrogen, and when you're drawing a covalent bond, you can either draw the electrons side by side like that, or you can draw them one on top of each other like that, as long as it shows that two electrons have been shared. Or, as in oxygen just below that, you'll see that two electrons from each oxygen are shared. So it's double, forming a double covalent bond. Okay. So sharing can be not only just one electron, it could be two or three depending on the scenario. Apologies for the sound effects. Right. Polar molecules. Now you have this over the page. So if you turn the page on, page
For
71. On 71 you have a page that says what is a polar molecule. Okay. So polar means an uneven distribution of electrons. 71. 71? This 71. Yeah. Okay, so as you can see here, we have some molecules that are non-polar, and that means electrically neutral. However, if something's polar, molecules like water molecules have a positive and a negative pole. And that means there's an uneven distribution of electrons. So polar means an uneven distribution of electrons. You see where it says what is polar? What is a polar molecule? You write in an uneven distribution of electrons. Okay, so have a look at this molecule here. Now I mentioned this before. This is our water molecule. Okay, so we've got two hydrogen and one oxygen. Now, when you look at the oxygen that was in your workbook just before, how many electrons should there, or what is the number? If you look at oxygen there, you can see that there are 8 electrons. We did it previously. Okay, so because there are 8 electrons circulating around oxygen, and how many electrons around hydrogen? Nice and easy. Hydrogen?
There should be 6 around oxygen and 2.
Yeah, no. Okay, so there's 1 electron on each hydrogen, yeah? But the cool thing is they have covalently bonded together. Okay, so we got this is oxygen, we've got the nucleus there, we've got the first orbit and the second orbit. So we've got 2 on the first orbit, and then 1, 2, 3, 4, 5, 6. Here's your 6. Okay. So those 6 are circulating, but then hydrogen brings 1 to the play. Okay. And now we have 1, 2, 3, 4, 5, 6, 7, 8 on that second orbit. Can you see that? Sort of? Yes? No? Maybe? Okay. Anyway, second orbit, how many electrons do they have to be?
2, 8.
Seconds.
8.
8. Good. So consequently, this water molecule is stable because we've now got 8 circulating all the way around. However, there are only 2 circulating around that hydrogen, only 2 circulating around that hydrogen, but there are essentially 6 circulating around the oxygen. So consequently, well, 8 but really 6, consequently there's an electron-hungry approach of the oxygen. So if it really likes electrons, and if you've got lots of electrons in the classroom, it will make us what? Positive or negative? Lots of electrons?
Negative.
Negative. So oxygen becomes negative, in contrast to the hydrogen, which really doesn't have as many electrons circulating. So we say the hydrogen is positive. It's really less negative, but it's more positive. And so consequently we create poles, uneven distribution of electrons. Now you know back in the day, in school days, you would have had those magnets that had a red side and a black side. You remember those big old-fashioned magnets? And if you held the black sides together, they would like repel each other, but if you flipped it over and went red to black, and they would go, yeah? Yeah.
But then if they're of similar charge, shouldn't they then be as opposed, opposite each other on either side as opposed to with carbon dioxide?
Like that?
Yeah,
Okay, wait, hold that thought. I'll get there in a second. Magnets first.
magnets.
Okay, so the magnets are also polar. So just like North Pole, South Pole, the magnets are attracted to opposite sides. Okay, so positive is attracted to negative, opposites attract. Now, as far as water goes, because of this uneven distribution, because oxygen has so many electrons, it draws that attraction of the negative capacity. It's called electron hungry. And so because of that electron hungry nature, it creates the oxygen being more negative. However, consequently, it pushes the hydrogen together, creating more of a positive spill on the side, instead of making it neutral like CO2 does. Because CO2 doesn't have the uneven distribution. As a result, the carbon and the oxygen just sit in a neutral capacity, in contrast to the hydrogen being pushed together as a result of not having as many electrons. And so why we get poles. Okay, so that is what polar is. Now polar, as such, creates our next type of bond we're going to look at, which is a hydrogen bond. Okay, and we're going to look at how hydrogen bonds form from one water molecule to another. So, turn back to page 69. And on 69 you'll see you have hydrogen bonds. Now hydrogen bonds are the weakest of all 3 bonds. Okay, so on description or on definition, a hydrogen bond is the weakest bond, so a weak chemical bond. Hydrogen is attracted to the negative portion of the polar molecule oxygen, which is known as an electron-hungry atom. So opposites attract. The electron-hungry oxygen is attracted to the positive hydrogen. And so if you look in your workbooks, you have a hydrogen bond shown there. And what it is just that dotted line from one oxygen to another molecule's hydrogen, and from another molecule's hydrogen to another molecule's oxygen. Okay? So essentially a water molecule looks like a frog. See? Frog. So that's one water molecule. That's one water molecule. That's one water molecule. And you notice how the eyes of my frog, positive, because hydrogen, positive, oxygen, negative. Now, to form a bridge from one water molecule to another, it has to go from oxygen to hydrogen. From hydrogen to oxygen. Okay? And the cool thing about hydrogen bonds is they're so weak that they break and reform and break and reform. So it's not like this bridge is consistent or continuous, because it's been broken, instantaneously reforming, been broken, instantaneously reforming. Okay, I'll show you a video. It will help make it work. Help make it sink in. Where is it? There we go.
It might just be the most universally known fact in chemistry, the chemical formula for water, H2O. A model of H2O doesn't look like much. Two small atoms of hydrogen, H2 part of H2O, attached to one bigger atom of oxygen, the O part of H2O. Kind of like a cartoon drawing of a teddy bear. And actually, water is kind of funny. Fun facts. Water, H2O, is the only natural substance on Earth found in all three common states of matter: liquid, solid, and gas or vapor. It's also one of the only common substances that is less dense in solid form than in liquid form. And water can dissolve more substances than any other liquid. Let's focus on H2O in liquid form. What gives water its remarkable qualities and abilities? It's all in the molecule's content and structure. Not just what each H2O molecule is made of, but how the atoms are positioned, in what configuration and shape, and how they are bound together. In water, just so you'll know for later, the H's and O's are held together by covalent bonds, by sharing electrons. H2O is a polar molecule. The same way our planet has north and south poles on opposite sides, the H2O molecule has two poles on opposite sides. And like a magnet, H2O has one positive end and one negative end. Thinking of that cartoon teddy bear again, the chin side of the oxygen atom has a slight negative electrical charge. The opposite side, the side with the two hydrogen ears, has a slight positive electrical charge. This might just be the second most universally known bit of chemistry. Opposites attract. The positive hydrogen side of every H2O molecule is going to attract and be attracted to the negative oxygen sides of other nearby H2O molecules in all directions. More and more of them pull closer and closer together until they're like people in a hot, crowded dance club. Packed so close together they can hardly move, but still turning and moving wildly. Molecules that stay close to each other are called cohesive, and water is highly cohesive. A pentillion, even hextillion of chaotically moving, tightly packed H2O molecules cohere to make a single raindrop. As good as water molecules are at all this cohering and convening, they also form bonds with surfaces and molecules unlike themselves, a force called adhesion, as in adhesive. Pour the water out of a glass, and the inside of the glass is still wet. Some H2O molecules stick or adhere to the silica molecules in the glass. Being cohesive and adhesive is what makes water a near universal solvent. How? Take salt or sodium chloride. Sodium ions, abbreviated as Na+, and chloride ions, abbreviated as Cl-, in a crystal. As soon as a salt crystal hits the water, it's rushed by a molecular mob of H2O molecules that break it apart, separate the sodium and chloride ions, kind of a chemical divide and conquer. Because sodium ions have a positive charge, each one is swarmed by H2O molecules flying at it with their negatively charged oxygen sides, completely surrounding the sodium ion, isolating it, carrying it off in a turbulent sea of H2O molecules. The same thing happens in reverse to the chloride ions, which have a negative charge. Each of those is surrounded and isolated by H2O molecules leading with their positively charged hydrogen sides. Each salt crystal is broken into tiny pieces, dissolved by and into the water. There's much, much more to know about H2O and how it works to keep every living thing on the planet and make other planets alive. And this video is a drop in the bucket.
Next to them. So you guys, for your ionic bond, write in the cation and anion as well. Cation and anion. I want to see those words there too. Yes. University entry across the board. So all universities, no matter what. Medicine doesn't, you would still have to do the medicine pathway, like so if you're looking at medicine pathway, Bachelor of Health Science.
Yeah, like health science.
Yeah, big one. It's still university entry. We generally feed like AUT, politics, things like that, because they're the major pathways for Bachelor of Health Science. However, Auckland Uni does do some health sciences as well, and because this is level 4, but it's university entry, so it's for all universities. And the key thing is, like when you approach AU or Otago, is to say, I've done a university entry certificate, and this is it, because they don't know us. They might do that now, but you know, it's a university entry certificate. That's kind of the theory. It's only certain universities that go, oh, it's CC or ACG. Yeah.
Taylor's College or like
No, it's English, yeah. Sorry. Well, yeah, so we're part of ACG as well. So we're now part of the Academic Colleges group.
Yeah.
But all you need to do is say it's a level 4 university entry certificate. And that's the stepping stone you need for those sort of universities. Because they recognise the fact that it's university entry, not the fact that who we are.
Okay.
Yeah. I mean, they know who we are, but it's the NZQA registered level 4 university entry certificate that they're looking for.
Okay, so we do get students who have a pretty strong background to say that to go for it, and how
To be honest, it will depend on the university as to what they're looking for. So the B plus average to a straight A average is with AUT, and it's a AUT board certificate that we offer, and so that's why we've got that connection. And so if you have straight A's, then you'll obviously feed all of our pathways, etc. However, with other universities, because we didn't buy the certificate off them, we bought it off AUT, so that's the connection. So it will depend on what you need and what you want to. But I mean, obviously, if you get straight A's, and it's a university entry certificate, they're going to go, ooh, pretty. Yeah. And so, like, if you want to go into medicine, I think that's the best way of doing it. Like, this is still university entry to get you into that. But I mean, even if you're coming straight out of school, you would still have to do that work as well, or whatever it is. So it's just that second step that's necessary. Yeah.
like I'm just straight out of school, yeah, like and then this job.
What's going on here?
So that's probably the best way of doing it. And like for the next, so if you're planning on doing January, February, like next year, is it only then? So then you need to look at what's going to help your application process.
That's the 8 protons.
Community work, or
it's not like a delta.
volunteer work, or anything that's actually medically that's not just going
I'm just wondering why it's moving like that.
Try and get something
that might
that's
just be a
going to
printing
be
problem. It doesn't normally do that. The nucleus is always
local
in
hospital and say, what
Like, ooh,
get
moving.
your foot in the door. And seriously, all universities just love that.
They all still pass
They
that.
lap up the fact that you're proactive in
They
your
all still
application.
pass.
But then in your application, you've got to really push the fact that you've done it. You know, so often you can create a CV or create an application. Like, you're too modest. Modesty is not a good thing.
in between these.
Kind of, show off. Exactly. Yeah.
And plus, after this semester, you have like another 6 months anyways.
Yeah. And so especially if you're straight out of school, you need
So if you got your Mickey Mouse head, and then it goes line, whatever, do another Mickey Mouse head. The hydrogen gets dropped.
So Sophia talked to you about scholarships. Oh, she did in the induction. Okay. So any scholarships apply all the time.
I mean, it's a bit long. These draw as many
Anything
lines
you
as
can, because
possible.
if there's something that you can go for, and that's the same modesty thing. Not only do you show off a little bit, but
As long as
or if you didn't do secondary school in New Zealand, then you know, how many years?
Like, 5 years.
Ah, really? Yeah. Well, then you don't need IELTS.
What if I drop top year 11?
Johnny,
Who
Rookie.
told you you would need IELTS?
I dropped.
So you did 2 years of primary and
I dropped out of high
secondary
school.
and high secondary.
I did.
Let me double check that
Year
because
11.
I'm pretty certain if you've done secondary school.
Like, I'm like,
Okay,
I
so
dropped
you
out.
guys, all of these questions, we have Deborah Spinetto from AUT coming to talk to us in week 10.
Okay.
And she is involved in the application processes for all disciplines for the health degrees at AUT. We've also got someone from Unitec coming to talk to us after her, also involved in the nursing disciplines from Unitec and the other disciplines for that matter. So those sort of questions, wait till she gets here, but I'm pretty certain, and I need to speak to Parks because I think he's wrong, that is if you've done secondary, if you've done secondary school in New Zealand, you shouldn't have to do IELTS as well. As far as I'm aware. IELTS, so English language. Yeah, but I mean that doesn't matter. It's kind of if you've done school here. So we've had students that were born in New Zealand, did secondary school in another country, but English was their first and only language. Like they didn't actually speak any other language, but because they didn't do secondary school in New Zealand, they had to do an IELTS. And it was like, but I don't speak anything. So yeah, that's a little bit wonky, but I'll confirm that. Can you remind me next week? I'll have an answer by next week. Thank you.
Marceline College.
10 electrons aren't they? Yes? Are they? Did you guys count?
Yes.
Okay, so there's 10. Does it say 10 there?
No.
No. So what does that tell you? It's got one. It's gained one. It's stolen one. It's whatever you want, whatever term you want to use. Plus, there's a minus sign. So that means it's gained an extra electron. So this electron from here, because there's only 2 electrons there, has come up here like this and has joined this one, making this. If that's a cation, this is a anion. And ion or anion. So negative, positive. What type of bond? Ionic bond. Very good. But now, because you were thinking that, let's do the next one. So. Sorry.
Yeah, it will.
So this was 9 and 2. Okay, so in this situation, you guys, you've got 2 electrons that are shared. Okay, so you have to color in the 2 electrons that are shared. And we know they are shared because how many electrons need to be in the first orbit? 2. So this guy brought 1 electron to the party, this guy brought 1 electron to the party, and so both of those electrons move around that atom there, making it stable. 2 electrons, first orbit. Okay? But now, how many electrons need to be in the second orbit for it to be stable? 8. So this guy brought that one to this party, and this guy had that one at this party, so we've got 2, 4, 6, 8, making it stable. So we know they're both shared, and so it makes them both atoms a covalent bond. They bonded to create that stability. Yeah? We agree? Mm-hmm. So you should have colored in both of those. Nice. Then we turn the page and we get to the cool stuff. Okay. So remember, an ion will only form with an ionic bond. Okay? Covalent bonding is sharing. Ionic bonding is the complete transfer. So our first bond we needed to outline, just a pen, is a covalent bond. So what would a definition for covalent be? Sharing of?
Between electrons.
Sharing of electrons. Good. Shared between atoms, not wrong, but sharing of electrons. Okay, so first off you had a hydrogen atom. All you had to do was draw a new electron. Okay, you know no bond has happened here because it was called a hydrogen atom. Okay, then a covalent bond occurs, and we draw in 2 electrons. And those 2 electrons are moving around both atoms, making it stable, because we need 2 electrons in the outermost orbit, or the first orbit, yeah? And those 2 coming from both atoms to make that hydrogen stable. Easy peasy? Cool. Now, ionic bonds. So what would a definition for ionic be?
Doing the complete retransfer from
Yeah.
another thing from
Deep.
Okay, well done. So, first off, you had the sodium atom and the chlorine atom. So for the sodium atom, you needed to draw in all 11 electrons. Okay, so it's 11p. So 2 on the first. 1, 2, 3, 4, 6, 7, 8. So 8 on the second plus 2 is 10, plus your 1 on the third. Okay, so sodium, oops, can't write, sodium atom, Na is all we need. If you put the whole chemical formula, you get a smiley face. Don't need it though, okay? Sodium atom like that. Then we had to do the chlorine as well, or chlorine, however you want to say it. So that was 17 here. Okay, so 2 on the first one. 7. 2, 4, 6, 7. Okay, so we've got sodium and chlorine. Don't put pluses or minuses on them when they're atoms though, okay?
Oh my gosh, I just did.
So this is the atom stage before a bond has occurred. Now, that one's not stable, that one's not stable. So, in the wording beneath that, it says sodium what? What does it do?
Loss.
Loses, gives, transfers, moves 1 electron to chlorine. Good. Becoming slightly positive. Now next to that, make sure you put in the word, what is it? Cation. Sodium becomes a cation because it becomes positive. Now, chlorine takes, steals, receives 1 electron from sodium, becoming slightly negative. Chlorine, Cl minus, so hence it's the anion. Anion. Good. And so then you had to draw in the ionic bond. So the next little drawing, you don't have that there, it becomes 11p plus, so sodium becomes positive, and then we have all 18 or all 8 in the outer orbit, and it becomes minus. Any questions? Is that feeling semi-okay?
Yes.
Sort of? Got it?
Yes.
Okay, so that's that one. Then turning over the page onto hydrogen bonds. Right, so our hydrogen bond, how do we need it? Okay, how would we describe a hydrogen bond?
The weakest bond.
Weakest bond, plus, ladies at the back who are gas bagging, give me hydrogen bonds. Nice. And what do we call oxygen? So it's electron hungry, lovely. Turn around, come on, you guys. Thank you. So, our oxygen is electron hungry. Sorry, the thing's running out. Hungry, oxygen. Dotted line, straight line, whichever you want. Okay, yeah.
Can you have both hydrogens from one molecule attached to a single molecule, so both hydrogen going onto one oxygen, or would they go to separate ones?
They could both go to one oxygen, however, they wouldn't continuously be attached at the same time,
Yeah.
necessarily. So they might, it's hard to say because the bridges form and break so repetitively that it might happen instantaneously, but then, yeah, not consistently. Ooh, bones. Have you drawn it? Look, you haven't even drawn it. Come on, draw it in. That's it. Yeah, so the big one is oxygen. The small little ones are your hydrogen. That's it. Yep, you got it. Oxygen to hydrogen, hydrogen.
You know, the more protons in each one, the bigger it is, yeah?
Another way of looking at it.
The more, whatever,
Oh, right.
the more biscuits you put in a bag, the bigger the bag will be.
Things have worked. So then you go.
I'm not really fast there. I don't have work, so it's on me. Yes, bad Johnny.
Damn.
So you guys look into diamonds. They have hydrogen bonds as well.
Do they? I thought
There we go.
oh yeah, that
Okay,
makes sense.
and on the next page.
What did you say?
Oh, no, it's fine.
No, before that.
Oh, diamonds, hydrogen ones.
Ah,
But they don't recycle it, like no coal.
yeah.
It's all like gas and stuff. You know when you look at stars in the sky, they're all over the place, yeah? But like if the stars are aligned like this,
Yes, exactly. So, you guys, on page 74,
then
you
it's
have more.
then that's what diamonds are. Layers. I suppose it's all like messy. isn't
Wait,
it?
you missed my pose. Anyway. Okay, page 70. You have another one. I want you to do that for homework, or if you've already done it. Oh, look at you. I love it when someone gets excited for homework. Okay, page 74, homework. Yes. And you have your compulsory homework quiz. Now, don't forget your compulsory homework quiz due next week. Every single one must be done. Seriously, I've had people cry this semester, even after I've told you. How many times have I told you you have to do every one? I am kind of repetitive, aren't I? Okay, so every question, it's an easy one. It's all on chemistry. Listen up before you finish up. It's all on chemistry, so go home and do it now because it will be really easy. And do page 74. We will check it in class next week, and we're going to do another page 74 in class next week as well. So you guys are going to be aces at this electron stuff by the end of it.
Do we need to remember the periodic table?
You need what, sorry?
We need to know the periodic table.
You do.
Oh, no.
You're going to sing the song for us next week.
Oh, no.
Voice diagram.
Yeah, take care of bro.
Oh, wait, your phone!
Kendall.